Okay, let's get started. So if you have a homework 5 to turn in, remember there is a homework due today. There's a growing pile of currently 3 people who turn in homework 5. If you have a homework 5 to turn in, go ahead and turn that in. If you haven't picked up your midterm, it's the left pile over here. And then the right pile is if you gave your midterm to me and asked for an update on your score because I graded it wrong. So pick up your midterms, please, if you haven't yet. Otherwise, are there any questions? So what's the plan? So we're going to do new material today, obviously. So what's going to happen next week? So Tuesday is review day. So what should you do for that? Yeah, send me questions by when? 5 minutes before the class starts? Sunday night, yeah. Or early Monday, yeah, that sort of thing. So by Sunday night or something, send me questions if you have any. And then I can think about what things are students concerned about, what things should I make examples for and go over in class on Tuesday. And then what's on Wednesday? The final exam. Is there class next Thursday?
No.
No. Is there class tomorrow? No, because it's Murica Day. So enjoy Murica tomorrow and then start studying for the test. Any questions about the final itself or anything related to it? Yeah.
Make sure you do have office hours.
Yeah. Yeah, so I still have office hours. Hopefully you won't bombard me on next Wednesday, but I do have office hours next Wednesday. Yep, yeah. The same way that you've been studying for the midterms. No, really. The midterms are meant to be a practice for the final because the questions will be of similar difficulty. Yep. It's just that you've seen the material before, so you should at least understand what types of things I'm concerned about and how I approach certain questions. There are no true, false, multiple choice on the test, so you won't have to worry about those. But the types of other questions are definitely fair game. Yeah.
Are there going to be questions that you've never asked us before on midterm?
Yeah. So my philosophy is to ask questions that have literally never been asked in human history.
I see. That's what I'm so.
Yeah, because that's something that I encounter every day and you will encounter every day in your jobs because you will encounter problems, I'm sure, that have never been looked at before and that no one's ever solved before. So that's going to happen. So if you start getting the habit of understanding how to approach things you've never seen before, that's a good thing. Okay. Other questions? Yeah.
The fourth question, how much writing do you expect?
So for all questions, you shouldn't have much writing. So there's a reason on every single question pretty much I wrote be brief in capital letters because I want you to be brief. Writing more can't help you. So if you wrote something correct and then said something incorrect, that's going to hurt you. So write what you need and don't write more. Writing more is not going to help. Just write what's needed. So all questions are not going to have very much writing at all. Yep. Other questions? Okay, so what were we starting to talk about yesterday?
EQCFG.
Yeah, EQCFG. So we're not going to get to this one just yet. So this is the one where we have CFGs and the language of one is equal to the language of the other. So they're equivalent CFGs. So we're not going to address this one just yet. So I'm going to do an intermediate problem before we actually get to EQ. So we're going to do all CFG first. So let's talk about all CFG first, which is the problem of given a grammar, determine whether or not it generates every string. Okay? So, and what did we actually determine about all CFG, or did I said about it last time? It was undecidable. So let's just use the fact the statement that it is undecidable for now. We'll prove it, but let's just use it for now. What can you determine about EQCFG because of that? Well, here's the idea. Suppose that we did have a way of determining EQCFG. So suppose it was decidable. Then what you can do is say, we can try to decide all CFG by saying the grammar that we got, just manufacture a grammar that generates every string, because that's easy to do. Then take the grammar that you were given as input and the manufactured one, feed both of them to the supposed decider for EQ. And then, if they are equivalent, then we know that the original grammar generated everything. And if they aren't equivalent, then we know the original grammar didn't generate everything. So, to decide, all CFG using a supposed decider for EQ. What you do is you take an input grammar G, where G is a CFG, and then we're going to make a CFG, let's call it S, where the language of S is everything. Then we run the supposed decider for EQ, CFG, on the G and the S. So the two grammars, the one that we were given to solve the all CFG problem and the manufactured one. So then if it says yes, they really do have the same language, then the original grammar does generate everything, which is the problem we're trying to solve anyway. So we need to say except here, and then if it rejects, we also reject. Which one? Yeah, my G's aren't very good. Yeah. Do you want me to fix all of them?
No, I get the point.
Okay. I'll fix all of them then. Yeah, it looks like a 6 actually in my opinion, so yeah. G wasn't the best letter for this. Okay. So this is the strategy that we outlined last time. So if EQCFG is decidable, then all CFG is. But I claim that all CFG is undecidable, so what can we determine about EQ? Anyone other than Andrew? So if EQCFG is decidable, then all CFG is. So if all CFG is undecidable, which is what I'm claiming, what do we know about EQ then? It's also undecidable because it's just the contrapositive. So if A, then B, the same thing is, if not B, then not A. So this implies EQ CFG is undecidable. Assuming all CFG is undecidable, which we haven't proved yet, but we will. But actually, all CFG is decidable. So be forewarned, this is not true. all CFG is decidable. So what you do is you take a grammar, and then you form the complement of that grammar, and then feed it into the emptiness test for CFGs, which we know to be decidable. Then we just invert the answer of what the emptiness test said. Because if it generated everything before, it generates nothing now. And if it didn't generate everything before, it does generate something now. And so now we can get all CFG. What's wrong with that idea? Take the grammar and then find the CFG for its complement. What's wrong with that idea? It's not closer to complement. Oh, so therefore, because that one test didn't work, therefore all CFG is undecidable. No, just because one way doesn't work doesn't imply anything. If we can prove that it is undecidable, then now we can claim that. So let's try to prove that it is undecidable. So let's prove that all CFG is undecidable, because then we can get the equivalence test also being undecidable from what we just did. Okay, so the way that this is going to go is kind of similar to the emptiness test for LBAs being undecidable. So how did we show that E sub LBA was undecidable before? What did we do? I mean, we did it yesterday, I think. Yeah. Yeah, so here's, I'll refresh your memory. So here's what we did. Well, if we looked at something called the configuration history of some Turing machine on an input, well, and we look at what are called accepting configuration histories, then where we end at in saying accept at the very end, well, the Turing machine can only have either 0 or 1 of these accepting configuration histories, because whatever happens, it either accepts the string or it doesn't. So what we did was we just built an LBA that recognized the strings of accepting config histories. So if there was any string in that language at all, then that must have meant that the Turing machine accepted that input W, because there was some string that encoded the machine being able to accept that string. And if there was no string in there, therefore the Turing machine did not accept the input W. So we were able to make that test possible on an LBA. And so therefore, we have this test between the language is empty or it isn't. And we can do it on an LBA. So supposing we can do it on an LBA, we can answer the same thing for ATM, which we know to be undecidable. So it's kind of the same idea here, where we're going to look at these config histories again, and instead of looking at just whether it has one accepting config history or 0, we're going to actually have a CFG be able to make all strings that are not accepting config histories. And so the difference here is it'll make all possible strings other than if there is an accepting config history. So if there is an accepting config history, then the CFG we're going to make doesn't generate everything. But if there isn't config history, then it does generate everything. So then if we have a test to determine whether or not the CFG's language is everything or it isn't, therefore we can know whether or not the Turing machine accepted the input, because it'll either generate everything but one string or everything. Anyone have questions on the idea? We'll get to the details. Okay, so let's look at an accepting config history again. and I'm only gonna kind of sketch this. So I'm not gonna look at every single of the details. So here we're going to assume that this is an accepting config history. So here the last one is an accepting config. The first one, of course, is the start config. And each step in turn yields the next one. So each one of these, of course, is a yield. So each of the steps is valid along the way. So if we want to make have a CFG make all strings that are not accepting config histories, well, what could go wrong here? So if I presented you this string and I claim it's an accepting config history, how can you show to me, oh, you're wrong. This is not an accepting config history. What can go wrong? What's that?
Any one of the three possibilities.
Yeah, any one of these three possibilities. So what can go wrong? A lot. What can go wrong? Well, the first config might not be the start config, right? It might not be. So first config might not be the start. What else can go wrong? Let's see. So the last config might not be an accepting one. So last config might not be accepting. I hope we're all accepting, but the last config definitely might not be. And then what else can go wrong? Well, the yield step might not work. So maybe like each of the configs is okay, but the yields is wrong in some place. Well, does it have to be wrong in every single place, or could it just be wrong in one place? Yeah, just one. So that's actually what makes this possible for CFGs, that some config does not yield the next one. So some config does not yield the next one. Okay? So if we can show that we can build a CFG for each one of these three, then it's just the union of the three together, and we know CFLs are closed in a union, so therefore we can make a CFG for the whole thing. So as long as we can make a CFG for each of the three, then we're okay. There's some minor details I'm skipping. So like some details might be, well, if you have, yeah, so like if it doesn't start or end with the pound sign, then it definitely isn't one of these. So like some minor details like that, but I claim we don't need to concern ourselves with that. So what about the first one? So the first config might not be the starting one. So how can I actually show that that's not context free? Well, so I'll actually just label these so that we can address them easier. So for the first one, where the first config might not be the starting one, well, let's see. Do we know what the start config actually is if we know the machine and the input W? Yeah, so it's just the start state followed by the string W. So if we look at the language of the single string Q0, W1, W2, up through Wn, it's just a single string. Well, what must happen is the starting config better be not this. So any string other than that, then it satisfies the first criterion right here. So, well, this is a finite language, and so its complement, therefore, is, well, not two. A finite language is, starts with an R and ends with egular. Regular. And what do we know about complement with regular? The close. So therefore, if we know that, then L bar is regular. So all strings that don't encode that particular string. So that's regular. Well, what we want is that we want it to start with a pound sign, but anything that is in L bar must come next. Because we assume that we handle the case where there's no pound sign on the front, but I claim we don't care about those. Well, what happens here is that if we have any string in L bar appear next, then the pound sign, and then anything else at all. So basically what I'm saying is I don't care what the rest of the tape is, as long as the first configuration, which is between the two pound signs, is not one of those. Therefore, it satisfies this first criterion. You got a question? Okay. So, and what do we know about this? Well, L bar is regular. So what do we know about this whole thing? Well, sigma star itself is regular, and concatenating a single character on doesn't really change anything. So the whole thing, in fact, is regular. And what do we know about regular and context-free? Yeah, regulars are always context-free. So showing us regular is actually even better. All we needed to show was context-free. Let's see. What about the second one, where the last config might not be the accepting one? So if we have a configuration here that is not the accepting one, well, one of two things that happens. Either we have two states in there, in which case we should only have one state in there, or 0 states in there, or the one state that is in there is not the accepting one. Yeah, so if we have a configuration, we have a configuration right here, and we have some string like this, where the state in the middle is not is not the accept state Q accept, then we want to actually encounter that. We want to accept these strings. Well, let's see. What could we do? Well, does it matter, other than the state, does it matter what the tape contents actually are, as long as the state is not the accept state? No, it doesn't actually matter. So the thing that we want to recognize is gamma star, so anything on the tape at all. And then inside here, the state that we want to see is anything other than the accept state. So anything from the set of states, take away the accept state. And then after that, anything on the tape. And then, more than that, if this is the very last one, then the very last character should be a pound sign, because this is the last one. And then before that, we can have anything before the pound sign before. Well, let's see. What is this language as a whole? Well, each of the pieces on each of the sides is regular, because it's basically just the same example as we did before. What about the thing in the middle? The states take away a state. Well, that's finite, because it's a finite set of states, and take away a state, that's a finite set. And what do we know about finite sets with relation to regular? Finite is regular, so we can just say it's regular too. And concatenation of regulars is regular too. And, oh, this is good. We get regular on the first two, which is actually more than we need. And remember, all we need is context-free. Any questions on those first two? Because the third one's going to be a little bit more substantial. Okay, let's look at tackle number 3. In fact, 3 can't be done on a CFG. Shoot. Why is that? The reason is, suppose we're looking at 2 configurations right next to each other. And we want to determine whether or not, say, C0 does not yield C1. Well, let's see. Well, right around where the tape head is, the contents of the tape might change. That's fine. But what about the rest of the string? Is that going to remain unchanged from one step to the next? Yeah, other than right around where the tape head is, it might change. But the rest of the tape contents is going to be exactly the same. So let's actually make this a little bigger. And let's just say that this is Q0, W1, W2, up to Wn. And then over here, maybe we moved right and didn't change the character. And we went to a state called Q, I guess. It doesn't actually really matter. Well, isn't this really, really, really similar to the language W$W that we've talked about before? Because the 2 strings on both sides are almost exactly the same. And what do we know about W$W? It's not context-free. Shoot. So what do we do? Wait. Wasn't there a language very close to W$W that was context-free? Where we reverse the right-hand side because the characters on the ends are the same, assuming that the tape head is not near the end. The contents are almost exactly the same until where the tape head is, and then we got to figure out what to do. But then the rest of the tape is the same until we reach the middle. And we don't care what happens to the rest of the tape other than these 2 configurations. Because if one of them doesn't yield the next, we don't care about what happens to the rest. So we don't need to worry about this one doesn't yield this one, and this one doesn't yield the next one. We only care about 2 consecutive ones. Okay, so let's talk about instead reversed accepting config histories. Adjective city here. So reverse accepting config histories. So it's the same idea as config histories where you have one, then a delimiter, next one, delimiter, next one, except here every other one is reversed. So C0 C1 reversed, so it's backwards, then C2 forwards, then C3 reversed. So every other one is reversed. CM, and maybe let's just assume for clarity that CM is forwards. But this works because every consecutive pair is essentially the reverse of the other string. So if we look at any 2 consecutive ones here, one of them is basically the reverse of the other. And so therefore, it's very close to the grammar for W#, the reverse of that string, which is really nice. The only difference now is, so basically we can do this with the grammar pretty easily. The only issue is, right around where the tape head is, we need to figure out, okay, we got to make sure that if the strings are not the same at any point along the way, so if they're not the same, then one doesn't yield the other. So, yeah, so what do we need to do? So if any character, I'll put not around, I'll just do this at a high level. Any character not around the tape head is inconsistent, then this is a string that we want to generate. This is a string to generate. So if there is a mismatch somewhere along the way, then one definitely does not yield the other one. So other than that case, the only thing that can go wrong that we want to take into account is that the transition that was applied was the wrong one, or it didn't apply it correctly. So, but the thing is that there's only a finite number of transitions that could possibly occur here. So then what we can do is just add a rule for each one of those possibilities. So only other case then is that the transition was applied incorrectly. But only a finite number of them. So add a rule for each. Okay? The important thing here is, do you understand why we need the reversed one, not just the normal one? So why did we do reversed again, instead of just doing the normal one? Right, because if we just dealt with the normal one, we can't do that with a CFG. Whereas with the reversed one, we can. Okay, so I'm leaving out some details, and the details are not important here. The important thing is, can we actually make a grammar that does not yield, that does not generate an accepting config history? Because if we can, then we can claim that all CFG is undecidable by just saying, if we just feed this grammar that we made into the decider for all CFG, then if it does generate everything, that means that there is no accepting config history, meaning that the Turing machine M did not accept W. Whereas if it does not generate everything, well, the only thing it couldn't have possibly generated is an accepting config history, meaning that the Turing machine M accepts W. So if all CFG is decidable, then we can solve ATM, but we can't solve ATM. So therefore, all CFG is undecidable. So how did we actually do this as a recap? Well, if we look at an accepting config history, well, the three things that can go wrong is the start config is wrong, or the accepting config is wrong, or one of the yield steps was wrong. So the first config, if it's not the start one, well, it better not be the start state followed by the input itself. Because if it is, then that step is okay. Then that step really is the start config. So, and then we saw that it was regular, which is more than we need. Then the second step, which is the last config might not be accepting, well, what can go wrong is that the state that's there is not the accept state. Because if it's not the accept state, it's not the accept config. So we just say, oh, it could be anything on the tape followed by any state not the accept state followed by anything on the tape, because when we want to accept, we don't care what's on the tape. So here we can just say anything and then anything after followed with a state that's not the accept state in the middle. And we saw that that was regular too, which again is more than we need. Then we saw what can go wrong is some config does not yield the next one. And we saw, well, we can't do that with a CFG really. So we introduced the reversed accepting config history, which allows us to do this with a CFG. And the reason is that we can generate the same characters on both ends. If one of the characters that is supposed to be the same really isn't the same, then we can actually detect that. So if the grammar just says, oh, I'm going to generate all possible characters where they're not the same on both ends, or they are the same until some point where they're not the same. So that can be done. Well, the only other possibility is they are the same the whole way except right around where the tape head is, and the transition was applied incorrectly because we want to detect when it's not an accepting config history. Well, I claim that there's only a finite number of rules that we need to add because there's only a finite number of transitions. So again, I'm not going to concern with the details here, but the fact that we can do this with a CFG implies that all CFG is undecidable. You had a question? Okay. Any other questions about this? So I would never ask you to prove something like this on the final, but it's just I want you to at least see why we were able to show that all CFG was undecidable. Because we're just trying to simulate a Turing machine on an input W. If we can simulate a Turing machine on input W, then that problem is undecidable because ATM is undecidable. So that's what I wanted you to really see, not necessarily the details. Yeah.
So, like you said, for exams, you would never ask us to prove this, but you would want us to know that.
Yeah, to know that all CFG is undecidable. So, like, if I asked you, for example, I wouldn't because we already showed it, to show that EQCFG is undecidable, then you can use the fact that all CFG is undecidable to progress there. And that's just a straightforward, if this one's decidable, then the other one must be. Other questions? Okay, so what we're going to do is we're going to take a short break, and then after that, we're going to work with some illicit drugs. Okay? So let's take a break.